we started out a little unsure about what we were going to do, whether it was this voxel compression approach or the dual marching cubes algorithm. And we sort of started on the first, and as soon as we understood that was going to be challenging and that we could kind of do this task level approach to both, we took the second approach.
One of the deciding factors for me was that the voxel compression code was about 5,000 lines of code, whereas the dual marching cube was only about 600. So it just seemed a lot more sensible to go for a smaller amount of code.
So both of those approaches were sort of adaptive in the sense that they used an octree, which I'm not sure if everyone's familiar with, but the Octree structure is where each top-level node is divided into 8 children, and each of those 8 children further divided into 8 children, and so on. So we were sort of skeptical that these kind of algorithms that were typically recursive would be able to get a lot of benefit from the GPU. So this was something quite novel for me, was that this idea of task level parallelism, where you could sort of have a naive understanding of the code, kind of leave it sequential. If you think of having 32 threads in a block, and maybe only using one of them, and it's doing some recursive sequential code, and then you just load a lot of those and run a whole lot of code sequentially. That doesn't have to be SIMD, it doesn't have to be in lockstep. One can run faster and one can run slower, and you can pipeline those. Since we had a naive understanding of the code for the dual marching cubes algorithm, it was not actually our code, and we had only recently started using that code. We decided to take this task level parallelism approach, make each thread do all the work independently. The drawbacks are that each thread needs basically to be able to do a whole sort of problem itself. So you can't fit that many on the GPU, but you can still fit quite a few depending on your problem size. So we were talking sort of 50 to 100 things all running at once on the GPU, whereas I'll get to the speedups and stuff later. You have huge kernels. The issues you get with trying to write all this stuff in a way that can run on the GPU means you've got a lot of code to try and get working. If you've got heap allocations, you have to take them all out. We started trying to use OpenACC and found that its support for some C++ stuff was not great. But yeah, it's quite intrusive on your code. Surprisingly, you sort of think, oh, this is going to be, I can just use my code as it is, but there are still some pretty significant changes to your code. And the benefits are that this is kind of applicable to all sorts of problems that you would think are not typically that good for a GPU. All that's really required is you have a lot of data, sort of at some very coarse level, it's embarrassingly parallel. The code structure itself can remain relatively similar. So after understanding the code a bit more, we realized that there was the possibility to do some fine-grained parallelism. That's something we sort of only came to quite late in the piece. You can only do that when you've got proper SIMD going on, single instruction, multiple data. Each thread does a lot less work, you have much less memory issues. Your kernels are smaller, you're sort of focusing on just a smaller subset of the code, hopefully. And we kind of got a fair way down the path with that, but we haven't quite got to the point where we've run this approach yet. And this is just talking a little bit about our sort of flip-flopping about how we're going to do this as things unfolded during the course of the week. So we started out with this idea that we'll do everything OpenACC only. It's the sort of easiest starting point. We just remove heap allocations, and then we came to realise that OpenACC couldn't compile one of the third-party library functions, Eigen SVD, singular value decomposition, that we were trying to do on the device. So then we tried to get CUDA building that part and linking, and we had some real trouble getting those to link. Eventually we ripped out the Eigen implementation and we replaced it with our own alternative, which was faster, just a couple of screenfuls of code, basically C code, and then went back to try and do OpenACC only, and that's when we realised we had all these other issues with using the STL. Like, even though we're not using doing any heap allocations, we were using like std array and just hash including the array header. Ultimately, it included some exception header file that included string, that included memory, that had some newing somewhere, and OpenACC just did not like it. So the upshot was, you really can't just compile OpenACC code for the device when you've got a whole pile of like that kind of STL stuff going on. I think that's sort of a to-do. You can't have virtual function calls. So we removed all these virtual function calls. We did a fair bit to try and get OpenACC working, but then you can't. There's still quite a few drawbacks to that approach. So then we went back to going purely with CUDA and building everything. So pretty much all the code was marked with device and host, it was a more pleasant experience. We were able to do much more that way.
The biggest problems we have trying to get the code running on the GPU was the Eigen matrix library, which was using the Jacobi SVD call to solve a overdetermined system of equations with 11 equations in 4 unknowns. And I thought that because that's a fairly small set of unknowns, it'd be appropriate to just use a Cholesky factorization and forward and back substitution. And as it turned out, that actually gave us a 3 times speed up in the CPU implementation, which was really nice. And that's the amount of code that was required to replace the Eigen library, so it was really worthwhile. And that just worked straight away with compiling that with NVCC, targeting the GPU. So another thing we needed to do was eliminate the virtual functions in the code, and one area where that was used was in the Octree nodes. There's a small class hierarchy there with an abstract base class and 2 derived classes. So we just replaced those 3 classes with a struct having effectively a tag union. And that also meant that we could just pre-allocate an array of nodes, because they weren't needing to be individually heap allocated, because they all had the same type. And doing that actually gave an additional 2 times speed up in the CPU implementation, just because probably a better cache locality.
So we were getting some crashes, or sometimes it was appearing to just stop. We weren't getting any seg faults and error messages, but it wasn't finishing. And we were incorrectly compiling with dash G, lowercase g, which is for NVCC is just putting debugging symbols in the host code. And so when we tried to debug with the CUDA GDB, we had very little information, and we just sort of stumbled around for quite a long time. It turned out that this was really a very trivial problem that I'd made. Once we got proper debugging in there, so dash capital G, everyone, if you're using NVCC, and dash line info, we straight away took us to the source of the problem, and relatively straight away found out what was going on. It was it was kind of so simple that it did take us quite a while to find it. It was like right up in main. Anyway, this is just a couple of observations we had. Like the first run after a compile was often taking a while, and we believe that there's some conversions going on. Our kernels are quite big, so when the kernel sort of gets transformed into some format that's ready to send straight to the GPU, and it caches that. So the first run was having this sort of big pause at the time of doing the first allocation, maybe 20 seconds or something, and then run it again, and it's just immediate. There's just also a note on optimization flags. You have to, I don't think that was quite the right syntax, but basically you can't just go -03. I think you have to do some optimization, a different switch to optimize the GPU. I think the default might be okay as long as you don't have debug symbols turned on. We had some issues with printf not being type safe, and a few red herrings where we were printing out. I forgot that it was %p and I was using %x, and we had two variables that were pointers that looked like they were completely wrong, and it was total red herring. Yeah, so some future work is to finish off this fine-grained parallelism and to extend our dual marching cubes implementation to work with a representation of the Hermite data that we have as input. So at the moment we're just using sort of an implicit scalar function.
So just with regard to going to a finer grained kernel, we observed that most of the dual marching cubes code is doing these 3 nested loops. So that's an obvious candidate for parallelism. The interesting thing though is in the innermost loop there's a call to a function which is recursive, because it actually can build an adaptive size subtree at that level, and the existing code has in effect a shared heap for allocating the nodes of subtree, and so that's a challenge for how to work out how to allow the threads of a kernel to be independently building up these subtrees, which I guess we'd basically have to allocate enough space, the maximum space they require. That would be one approach, but that does mean that using up a lot more memory that way when you've made each one have enough room for it to grow into based on the worst case situation. So that's how we would probably write the kernel, using grid stride loops, so it can easily change the number of the dimensions of the grid and blocks.
Cool. Thank you.